So this is the second of two lectures dealing with the history of algebra. This one in particular looks at algebra in Europe from the late 18th century onwards, and how people shifted away from simply trying to solve equations into thinking about how to characterize those equations which are actually solvable. So this fits into a lecture course of 16 lectures, which aims to give undergraduates a flavour of the history of the mathematics that they've met in their 2 years in Oxford prior to this. So it can't hope to be a comprehensive history. So the story we're trying to tell in these two lectures on the history of algebra is one based very much around equation solving, taking us up to the edges of Galois theory. So there are certain things that don't appear here. Indian contributions to algebra, Chinese contributions to algebra. These are dealt with to some extent elsewhere in the course, but hopefully this is something that we're going to look to include in these lectures in the future. I'm going to pick this up from exactly where I just finished off, actually, so with Lagrange. And so we're going to move the story into the 19th century, have a look at what Lagrange says and what that sparks in terms of people studying the solution of equations, the theory of equations, and then how that gets into more abstract things like group theory and other parts of abstract algebra as we get towards the end of the century and into the 20th century. So as I say, we'll start with Lagrange, and then we'll turn to Cauchy, because even though we're not talking about analysis, we don't get away from Cauchy. So he has ideas about what he terms substitutions, and I'll say what that means in a minute. There's a sense in which some of the things that people are working on at this stage mark an end to this, what you might call the classical theory of equations, about 1826. And then groups start to appear. So Galois and Cauchy are the two big names in this connection. Symbolical algebra is a slightly odd sideline that we'll have a look at that doesn't really go anywhere. And then at the very end, I will say something about the emergence of modern abstract algebra. I won't dwell on that too much because I know it will contain things that people won't have necessarily done the courses for. So we're not going to go into any of that maths in any great detail. One thing to mention first of all, though, is that something is happening in the 19th century where there is just a sort of general trend towards greater abstraction in mathematics. So what we're going to see is permutations appearing and being treated as mathematical objects in of themselves. So something that is not a number, something that is not a function, it is a function, but treated in a more abstract way. Later on, we'll see things like matrices similarly being treated in this same way. It's a new mathematical object. And gradually over the century, people are also starting to think not just about the individual elements of systems, but the overall structure of the system. So we'll see that here in the case of groups, for example. Okay, so back to Lagrange and his 200-page reflections. As I said, he's the one who gives us this assertion that nothing much has happened in the past 2 centuries. But he spends this text, as I say, identifying or trying to identify a common thread in all of these prior methods, and he settles on the idea of the resolvent equation, the reduced equation. And he's also quite interested in permutations as well, and they will have a role to play in a second. This is how Lagrange proceeds. So he's looking at roots of an equation, functions of roots of an equation. So suppose we're trying to solve a cubic equation. We can write down the roots x1, x2, x3. We don't know what they are. We just know that there are 3 of them, and so we just write them down, x1, x2, x3. And then we can set up some function of those roots. So y is quite clearly a function of x1, x2, x3. It's got this alpha in there, which is a root of unity. And what Lagrange notices is that interesting things happen if you permute the x's amongst themselves. So if you permute the x's amongst themselves, y only takes 6 values. There are only 6 possible different values of y. But he goes further and he notices, like some of the examples that we had before, that okay, it's a degree 6 equation, but it's actually quadratic in y squared, in y cubed. So looking at that a different way, y cubed only takes 2 values while we permute x1, x2, x3 amongst themselves. So y cubed satisfies a quadratic equation. And this is the resolvent. So we started with a cubic, we've got down to a quadratic, which will be our resolvent. In theory, we know how to solve the quadratic, so we do that and then we go back up to solve the cubic. And Lagrange really sort of pulls this out as a thread that is common to the methods of lots of the previous authors. He says essentially they all reduce to this. And he does a similar thing for quartic equations. So again, we want to solve a quartic. Let's call the roots x1 to x4. And then we can write down this quantity y, which is a function of x1 to x4. And Lagrange notices that this only takes 3 values when we permute the x's amongst themselves. So y satisfies a cubic equation, and if we can get hold of y, we can start to get hold of the roots of the original equation. And there's more than one way of doing this. So there's more than one route to a resolvent equation, which is not unique. So another example is z here. Z squared takes just 3 values when we permute the x's. So again, z squared satisfies a cubic equation. So we've still reduced the quartic to a cubic. So this suggests a way forward for Lagrange. Can we do something like this in higher cases? So he notices that things tend to fail when people try to do this with the quintic. So he sort of tries to adopt a more general point of view and see what you can do. So he takes a degree n polynomial, he writes down the roots x1 to xn, and he proves the theorem, which is that if we take some function y or f of those roots, then y is a root of an equation of degree m, where m is the number of values that is taken by y when we permute those roots. So just extending what he was doing before into a more general setting. Then he goes into, on the back of that, he concludes the number of values of f will always be a divisor of n factorial. So we've got echoes of Bezout's hypothesis here. We've also got something involving permutations and something involving n factorial. So hopefully this is looking slightly suggestive at this stage. So it's a really nice proof. Sorry, let me say that again. It's a really nice theorem. The proof is not, however. The proof, it has errors. A lot of it is proof by example, but it can be patched up. It does work. And if you haven't already guessed, this sort of morphs through various different mathematical languages and ends up as what we would now call Lagrange's theorem in group theory. It's written in the form that he has it here because there is no language of groups at this point. Nobody has come up with that idea yet. So he's identified the resolvent and permutations as useful tools in trying to tackle higher degree equations. So for the quintic, okay, so Lagrange has proved in general we might end up having a resolvent of degree 120, which is not really much use to anyone. But he notices that we can bring this down in the way that Bezout hoped we could. So if we call the roots x1 to x5 and we look at this quantity y to the fifth takes only 24 values when we permute the x's. So y to the fifth is satisfies the resolvent equation of degree 24. Still not great, but better than 120. And in fact, you can do more things along these lines to get it down to 6, which is quite an impressive reduction. The question is, can we get it any further? Because 6 is still too high. So what can we do with that now? And this is where Lagrange pretty much gets stuck. But other people pick up the ideas and see how they can run with them. One of those is Paolo Ruffini, who's an Italian mathematician, and he's read Lagrange. He looks at the case of n equals 5. He shows that a function of 5 variables cannot take 3 or 4 values. He does this by exhaustively looking at every possible permutation in every possible case that can arise. he claims on the back of this to have proved that equations of degree 5 are not solvable in radicals. There is an issue, slight issue with his proof in that he sort of has done this, but only for the case where you insist on the resolvent having rational coefficients. So there's a bit more to do. He seems to have sent this work to Lagrange. Lagrange never replies. There are hints in Lagrange's later writings that perhaps he wasn't impressed, but he doesn't seem to have ever actually replied. And on it goes. Ruffini's style is quite obscure. People were just not convinced about the things that he was writing, and there's still something of that nowadays. People are still doubtful about whether he did what he claimed to have done or whether it goes far enough. The other person, or one of the other people who was influenced by Lagrange, is Cauchy. So this is in a paper that he wrote in 1812 when he was just 23. So this is one of his early papers. And if the French readers might notice that this is very definitely in the same vein as what Lagrange was doing. So memoir on the number of values that a function can take when the values it contains are permuted in all possible ways. And to analyze this problem, he sets up some notation, some terminology for a theory of substitutions. And what he calls a substitution is what we would call a permutation. Just to confuse matters, he did use the word permutation, but for him, a permutation is a static arrangement of the elements of a set, and a substitution is the passage from one permutation to another. So we probably use permutation for that, but he uses substitution. But essentially, it's the same idea. And he's thinking about numbers of values of functions. So he's got a function of little n variables. It takes capital N values, and he puts some bounds on capital N. Interestingly, it's a result that involves a prime number where we're not talking about the biggest prime or any prime that divides n. We're talking about a prime less than n, which is slightly peculiar, but I mean, that's what the result is. And he conjectures that if n is greater than or equal to 5, then one of these two options holds, and manages to prove this for n equals 6. So he's sort of homing in on the n equals 5 case a little bit more. And this is one of the things I had in mind when I said at the beginning that there's greater abstraction entering into mathematics. So he's treating these substitutions as mathematical entities unto themselves that can be operated with as a unit, as a thing in itself, rather than being broken down into numbers or anything else. So I'll come back to Cauchy shortly. The third person, though, I want to mention who picks up Lagrange's ideas is Abel. So he takes up this problem in about 1820. By 1823, he's found a solution that he wants to find, publishes it in a sort of self-published pamphlet, and then it starts to spread a bit more widely. And he's picking up very much on the idea of permutations. It's published in a sort of more respectable format in Kreller's journal in 1826. Now, Kreller's journal is slightly different from the other journals that have been mentioned so far in the course. So I've mentioned academic journals appearing that give a sort of stamp of approval to papers that were published, and they're all very much based at universities, academies, and so on. Kreller's journal is different. This is a commercial venture. This is a sort of commercial publication, which nevertheless goes on to be one of the big and very well-respected mathematical journals of the 19th century. So for n equals 5, Abel refines Cauchy's theorem and then uses that to prove, finally, that there is no general solution of a quintic equation in radicals. That is, there is no formula for the solution. And so this is the point at which I would argue that we've sort of reached the end of classical algebra, if you like. We've reached the end of where people are trying to find solutions to equations or manipulate the equations or learn about their structure. Something different is going on here. So much so that a lot of people across Europe, particularly in Britain, have a hard time accepting this result because it's something new. We're not doing something constructive and proving that such and such exists. we're proving an impossibility, which is a really kind of new idea for people to get their heads around. But it prompts new questions. So very naturally you would ask, well, okay, if I can't solve every equation, which ones can I solve? And so maybe we should start looking for criteria for solvability of equations. And this is where Galois appears, probably a name that's familiar to everybody for the romantic stories that have grown up around him, his involvement in revolutionary politics, his dying in a duel at a young age and furiously scribbling on manuscripts, mathematical manuscripts the night before. There's a seed of truth in this, but don't believe everything that you read about Galois. So Galois certainly had read Cauchy. So through Cauchy he knew about Lagrange. He might have read Lagrange independently anyway, but Cauchy refers to Ruffini, so Galois would have known about Ruffini's work, at least in overview, through Cauchy, but he probably didn't know about Abel. So he's coming along, he doesn't yet know this proof of the unsolvability of the quintic. But he's asking this natural question of when are polynomial equations solvable? What can we find criteria for them? And it's exactly what he has in his title here. So this is a memoir that's come to be known as the Premier Memoir. It has a slightly tortuous publication history, which I'll come to in a second. But this is where he outlines some criteria for solving equations in radicals. And if anybody's doing the Galois theory course, you will be seeing these ideas from a slightly different perspective. Is that this term? I can't remember. Next term, okay. So next term you might see these ideas from a slightly different perspective. Okay, so he produces this manuscript. He sends it off to the Paris Academy, and then there's this story has developed around Galois of him being an underappreciated genius and so on, and everybody rejects his work, and it's not quite like that. Cauchy read the work. Cauchy gave advice on the work. I mean, it was a bit of a mess. So Cauchy advises Galois on how to reformulate it and resubmit to the Academy, which he does very soon afterwards. They go to Joseph Fourier as secretary of the Academy. He promptly dies. I don't think there's a connection. And then the papers go missing. So Galois writes it all up again from memory, resubmits to the Academy, and it's rejected by Poisson and also Lacroix. I haven't put his name here, but they read the paper. They can't quite make much of it. They sort of understand what he's doing, but there's a sense that he's come up with this condition for solvability of equations, but it's not quite usable. It's not refined enough to be something that's publishable. So he's naturally quite upset about this, but he keeps on working on the papers up to the point of his death in a duel. And we should be sympathetic to Poisson and Lacroix because Galois didn't actually explain everything in this memoir. So nowadays, in order to read it, you have to read it in conjunction with a letter he sent to a friend of his, Auguste Chevalier. This sort of testamentary letter, lettre testamentaire, is essentially explains the things that the memoir doesn't explain, including what a group is. And so all of Galois' papers go to Chevalier after Galois' death, and he wants Chevalier to be his literary executor, and to try to get this material published, try to get somebody to make a judgment, not necessarily on the accuracy of the ideas, but on the importance of the ideas. Okay, and this is not the only thing that Galois did. He's active in some other areas. So, okay, as we'll see in a second, he came up with an idea that we now identify as being a group. He did some work on fields, particularly finite fields. In connection with the group, we've got the idea of a Galois group, which you'll learn about next term if you take that course. So we associate a group with a polynomial, and you can study the group to tell you about the solvability of the polynomial. We've got necessary and sufficient conditions for that solvability. And then he looks at equations of prime degree as a sort of an application of these criteria, just to give a demonstration of how they work. So this is the first page of the premier memoir, or one of the first pages, sorry. And so this is I'm not quite sure how big, but very, very large piece of paper. And what Galois liked to do is fold it down the middle and do his main writing on the right-hand side, and then fill in extra things, extra notes on the left-hand side. And this sort of the kind of margins that Fermat could only dream of. And so on this page, he gives his proposition 1, and this is how he's relating a polynomial to a group. He doesn't actually define what he means by a group. That then appears in the marginal notes, and he's a bit inconsistent and uses the word in a couple of different ways. So we can forgive his readers for, his early readers for not quite knowing what was going on. And this is one of the things he's working on right up to the evening before his death. But what you probably can't quite make out there is he's writing about substitutions. So he's taking Cauchy's language. So a substitution is the passage from one permutation to another. The permutation from which one starts doesn't matter. Well, that's fair enough. And if we got some collection of permutations that we're interested in, or substitutions that we're interested in, I should say, and we've got two substitutions, S and T, then the composition ST is also in the collection. So he's giving us a closure property. And another exercise for you to try later, if you've never done it before, this is actually enough to define a group in our sense, if we're dealing with permutations. It's in the abstract case we need a few more conditions, but for permutations this is fine as a definition of a group. And as I said, there's a slightly prolonged history of the publication of Galois' results. So this early work that relates to finite fields is actually published formally. So this is work that he does get out there and get published. We've then got the Premier Memoir and the Testamentary Letter. Eventually, 1846, Chevalier hands over all these papers to Louville. Is it Joseph Louville? And Louville is somebody else who has founded a journal as a commercial venture. So Louville's journal becomes another one of the big 19th century mathematical journals. So Louville's is the one based in France, Kreller is the one based in Germany, and so they're both major fora for publishing mathematics in the 19th century. And so Louville publishes all of Galois' papers in 1846. So this is the first time that people more widely have access to these various ideas. It then goes through umpteen different versions by different people, but I can particularly recommend this last one, which was the first full English translation of them by Peter Neumann, which was published on Galois' 200th birthday. So if you want to get more of an idea of Galois' ideas, this is where I point you towards. Yeah.
Did Chevalier go to the Paris Academy and it was rejected, or did he give up on that and go straight to Louville?
That's a good question. I think he might have gone straight to Louville. I'd have to check that, but I think probably that was seen, as you say, as a path that had been tried and that didn't work out. Okay. So Galois developing these ideas. I've not said a huge amount about his nature of his group, but it's a group of permutations, and there's a closure property. This is the thing that he's emphasizing. Meanwhile, just the year before Louville publishes these ideas, Cauchy, who had looked at these ideas relating to substitutions in 1815 or 1812 to 1815, had then set them aside and not done anything else with them after this point. But in 1845, a man named Joseph Bertrand sends a paper to the Paris Academy that builds on Cauchy's work of 1815. And it's given to Cauchy to referee in the April of that year. And this really sparks something in Cauchy, and then he goes on produces this stream of papers over the next few months on ideas relating to permutations, the structure of collections of permutations. This is in the Academy journals and also as we'll probably see more clearly in a later lecture, his own journal. I mean, he was so productive as a mathematician, he ended up establishing his own journal, essentially just to publish his own work. I think having a father-in-law who was a publisher helped with that. So in the November, he finally gets round to giving a report on Bertrand's paper, which is then eventually published in 1848. So there's a sort of distorted chronology of ideas here, but there's this stream of papers coming from Cauchy on the subject of substitutions. And what he does in there, among many other things, is he develops ideas very similar to what Galois was doing. So he looks at substitution, so he's using the two-row notation that we tend to use nowadays. Sometimes he reads them from bottom to top rather than top to bottom, but it's essentially the same idea. And he's also thinking in terms of generators, although that's not the language that he uses. So he's got some basic substitutions. Anything that you can get from combining those in all possible ways is what he calls a system of conjoined substitutions. Sometimes translated as combined substitutions, sometimes as conjugate substitutions, but I've avoided the word conjugate because, of course, in modern group theory, that means something, so it's probably best avoided here. And where he's going with this is he's going back to these Lagrangian things. So for a function of n variables, he's looking at the substitutions that leave the function unchanged as a way of counting the number of values that the function can take. And he's sort of thinking in terms of the index of the system, which is going to be the order, and it's a factor of n factorial. So it's all fitting in very neatly with the sort of things that Lagrange was saying, almost giving it a framework, more of an abstract framework. And so then this leads him to proof of that conjecture from 1815, which relates to the unsolvability of the quintic. But by 1846, his papers have sort of dried up. He's moved on to other things. And this, of course, is the year, as we just saw, in which Louville publishes Lagrange's paper, Galois' papers, sorry. And thereafter, they're sort of Cauchy's ideas, Galois' ideas on similar subjects are sort of out there in the public domain, and they're increasingly woven together as the decades pass. And various people think that this is an important area of mathematics to develop, and Cauchy certainly. So jump ahead a few years to 1857, and the Paris Academy would often set prize questions for people to have a go at. And this is what they set, possibly at Cauchy's, under Cauchy's influence in 1857. So what are the possibilities for the number of values of well-defined functions containing a given number of letters, and how can one form the functions for which there exists a given number of values? So it's very much still in that kind of counting the number of values of a function kind of vein. There are 3 entries for this prize. So Émile Mathieu, Camille Jordan, they submit their doctoral dissertations. Those are 2 people who go on to be quite big names in group theory later in the century. And then we've also got the Reverend Thomas Pennington Kirkman, you might know from work in combinatorics. This is what he's best known for. But he's a Cheshire clergyman who often presented his work to the Manchester Literary and Philosophical Society alongside talks about local butterflies. So you really do have to wonder what that audience made of this work. But anyway, and he's quite idiosyncratic. I mean, Mathieu and Jordan are writing in a style very much like Cauchy and Lagrange. Kirkman has his own style entirely, and so people do not find him easy to read. None of these people were deemed to have written enough to win this prize. Kirkman, for one, is very bitter about this for many years afterwards. But interestingly, they all interpreted the problem in the same way. Find all the subgroups of the symmetric group on n letters. So there was no winner here, but it stimulates people to think about these things a bit more. So Mathieu and Jordan go on to do other things. Kirkman goes on to do other things as well. And it begins the development and consolidation of a theory of finite groups. It helps this merger of the slightly different but very, very similar approaches of Galois and Cauchy. So really bringing the theory together. Just a few years after this, so 1866, a man called Alfred Serre published an algebra textbook where we have a presentation of Galois theory for undergraduate readership for the first time. So these ideas are really getting into the mainstream. And of course, in thinking about groups, this structural approach is beginning to take some hold as well. I'll come back to that in a moment. Before I go on to the abstract algebra of the later century, though, I just want to pause for a moment and go into one of those sidelines that I think I've hinted at, which I find quite interesting. I think I mentioned it in an earlier lecture, this idea of symbolical algebra as something that people in Britain were thinking about around about 1830. Doesn't really go anywhere, but it's quite interesting as a lens on what people are thinking, how people are thinking about mathematics in Britain at this time. So this is symbolical algebra as distinct from the symbolic algebra, the sort of symbolic notation that we've talked about previously. So this is a response to certain people in Britain who, around the sort of 1790s and a little bit later, are disputing the notion of a negative number. They're saying they should be rejected from mathematics altogether. And in some cases, they do have good points. So that at the heart of their criticism is a pedagogical one. The way in which negative numbers are presented to school children. They don't like the way it's done. They don't like the fact that there is a subtle difference between the minus sign that appears in things like A minus B and the minus sign that you stick on the front of something and just write minus C. There is a difference there, and he doesn't. The people involved in this don't think this is being handled very well, and then they sort of reach for the extreme of saying, well, let's just reject them from mathematics altogether. So William Friend is a man that I'm thinking of in particular in this connection. He writes a treatise of algebra in the 1790s where you don't use negative numbers, and it goes back to Cardano in a way, in that we now have to have case-by-case solutions of equations because there are now different types of equations depending on where the terms lie in relation to the equal sign, because we can't have negative quantities, and so on. So these people are, in some ways, a little bit of an embarrassment. This is a time when people, beginning, 1810s, people are starting to think there's all this really nice analysis going on in France. We don't have access to that. Nobody in Britain can barely read this material. And so they're starting to import continental analysis. So people trying to reject negative numbers is, slightly embarrassing. So there is an attempt to respond to this criticism, to really sort of create a framework in which you can explain away these apparent difficulties. And one of the first attempts to do this is by George Peacock, who's a Cambridge mathematician, one of the people responsible for bringing continental analysis into Britain in a big way, and in particular inserting it into Cambridge mathematical tripos exams. So his treatise of algebra is a response to this idea. And so the idea is that he separates out arithmetical algebra and symbolic algebra. And arithmetical algebra is, well, it's arithmetic, really. All the symbols always stand for positive real numbers. So you always, if you're writing down something like A minus B, you always have to be careful that A is bigger than B and that kind of thing. And then in symbolical algebra, this is where we focus more on the rules of what we're doing. We don't worry about what the symbols actually stand for. It's the rules that matter. And it's only at the end of the process that we worry about interpretation, if we care at all. So rules are the key. And this in turn gets criticised because it's got echoes of Newton's moments. So how can you do algebraic manipulations with quantities that then are given interpretation that was not consistent with what you were doing earlier? So it's very much like the divide by this quantity and then set it equal to 0 at the end. So it's the same sort of arguments appear here. But a lot of people are quite happy to go with this. A lot of the familiar names here sort of go with this idea. And one of the foundations that Peacock lays down is that you will always have a model for what you do. So arithmetic will serve as a model for a version of symbolical algebra. So your symbolical algebra will model arithmetic in that all your operations will be commutative and so on and so forth. So he doesn't write down an axiomatization or anything, but it's starting to look like the way we would axiomatize a field, say, that kind of thing. But it doesn't actually go that far. But Boole writing on logic, De Morgan writing on algebra, Hamilton writing about quaternions, they sort of come out of this tradition in a fairly indirect way. So not much of it survives, partly because here we have a system of algebra that says, well, we can choose the rules, whatever rules we want to work with, and work with the system that arises from that. But most people are saying, well, why would we want to do that? You know, why would we set down arbitrary rules and work from there? So it sort of dies out to some extent, but survives in a way in terms of the language that people are using. So when Hamilton's writing about quaternions, there's something of the language that harks back to symbolical algebra. And the reason I bring this up here, not just as an example of something that doesn't quite go anywhere, the reason I bring it up here is that Duncan Gregory was a Cambridge tutor, and he had one particularly famous student, namely Arthur Cayley. And so Cayley, you might have seen in the reading, is often credited with coming up with the first abstract notion of a group. And in doing that, possibly there's some legacy of the symbolical algebraists sitting behind him. So Cayley, as you know, probably know, is interested in lots of things right across mathematics. And he's looking at a particular curve called the caustic, which is a curve you get if you've got a sort of reflecting cylinder, sort of reflective on the inside, fill it up with water, shine a light across the top, and then you'll get a certain pattern of light on the surface of the water. I have to admit, I'm not entirely sure why he was interested in this, but this is what he was interested in. And he's describing this mathematically, and he notices that you can make certain transformations of this curve. And what he also notices is that you take two of these transformations and you compose them, you get another one of these transformations. So there's a closure property in this collection of transformations, I think 6 of them in total, that you can apply to this curve. And so he starts to notice that this actually is a structure that is appearing elsewhere in mathematics. And he sets down this definition. So a set of symbols, 1 alpha beta ... all of them different, such that the product of any 2 of them, no matter in what order, or the product of any one of them into itself belongs to the set, is said to be a group. So he's emphasizing the closure property. This is next week's essay, so I'm not going to go into this in huge detail, but you might already have sort of warning flags going up that this perhaps doesn't quite work as a definition of a group from our point of view. And that's something that we will get into next week. But yes, there's a bit more needed here, but it is sort of elsewhere in Cayley's paper in sort of interesting ways. What he's got here is essentially Galois' definition, closure and nothing else. And he does attach a footnote to the word group and says this is a word that I've got from Galois, essentially. He never explicitly mentions Cauchy, as far as I can remember. Possibly he had read Cauchy, he was reading those sorts of journals, so he might have seen Cauchy's papers, but I don't know. And so because of this, Cayley is widely attributed with introducing the abstract notion of a group. This is a point that I think we'll probably end up discussing in the classes next week, perhaps in a similar vein to our discussions about calculus before. So in terms of attribution and how good was the definition? Are we prepared to give him this credit or not? So certain things that perhaps we could say are in his favour, though, is he does some interesting things with this that we might recognise as being reasonably group theoretic. So first of all, the big thing is that he's identified this structure and he's found it in other places, all over the place in mathematics. So permutations, as in Galois, transformations of a caustic curve, where Cayley is coming from. But then he says, well, we can think about roots of unity. There's a group structure there. We can think about other collections of elliptic functions, quadratic forms. We can find group structures there. Collections of matrices, we can find a group structure. So this is a structure that suddenly is everywhere in mathematics. And as we'll see in a couple of weeks, matrices are a particularly important example for Cayley, because that's another thing that he's credited with inventing. So we'll come to that. And so he's thinking about different orders of groups. Certainly they're all finite in his case. Thinking about symmetric groups, groups of permutations, and back eventually to this system of transformations of the caustic curve. And he's quite interested in the question of how many groups are there of a given order. And he works this out for some low orders. As you might know, this then in the 20th century goes on to be quite a big question in group theory. How many groups of a certain type are there of each order? But these ideas don't really catch on very much at first, and it's a similar attitude, I think, to the attitude towards abstraction in other instances, which is that, okay, yeah, great, this structure is everywhere, but what can we do with this idea? We are perhaps more comfortable working directly with elliptic functions or working directly with matrices. Why do we need this overarching abstract theory? So it takes a while to catch on. Doesn't catch on so well in Britain, but eventually it does catch on more in Germany, possibly because there's a sort of structural algebraic thing going on there already, which we'll see in a second. And so Cayley keeps promoting the idea. So 1878, this is an encyclopedia article that he writes on this topic, in which he tries to boil the idea of a group down to the very essence of why this is an important idea. So a group is defined by means of the laws of combinations of its symbols. So we don't care what the elements are, it's the rules of operation that matter. And so when these German algebraists are picking up this idea, pretty much immediately after this, a lot of them are adopting this as a kind of mantra, as a sort of quotation to put at the head of a paper, as to say this is how we're thinking about these groups. We're emphasizing the rules, we're emphasizing the laws of operation above any consideration of what the elements look like. Kronecker in Germany is one of the people who's picking up on these ideas. I think slightly independently of other developments, he hits upon the idea of what we now call an abelian group, because that's coming out of things, number theoretic things that he's doing. But the first attempt at an axiomatization of groups, so this is not something that Cayley was doing. He doesn't give an axiomatic definition, but we've got the sort of axiomatic tradition developing in Germany in the sort of later years of the 19th century. And one of the authors in that is a man called Heinrich Weber, who writes several papers in this area, eventually goes on to write a fairly substantial 3-volume textbook on algebra that really sort of summarizes where things stand at the end of the 19th century. And so he defines a group like this. So he's taking a system of elements of any kind, theta 1 to theta h. So this is a group of degree h. So he hasn't used the word finite, but implicitly this is a finite group. And then we've got this, what I always find slightly peculiar first axiom, where he just sets out the fact that there is an operation on them. I'm not sure this says anything more than that. Whatever this operation is, it's associative, as we would hope. And then his third condition is that, well, first of all, if theta times theta r is equal to theta times theta s, then we can cancel the theta and conclude that theta r is equal to theta s, and then the other way around as well. So it's a cancellation property. And if you have ever been made to play around with group axioms, possibly when you were doing group theory in the first year, you'd know that this is enough for a finite group. So again, like Galois, it doesn't quite look like our definition of a group, but this is actually enough. You can deduce the existence of identity and inverses from this definition in the finite case, and later on other people find it more useful to include those explicitly as axioms, particularly as people start thinking about infinite groups as well, because this doesn't work in the infinite case. You can't make that deduction there. But finite and infinite cases were dealt with quite separately to begin with, and then when they're rolled into one at the end of the 19th century, some tweaks to the definition are needed, so to make sure that it covers all cases. And there are a couple of papers. You could maybe tell from the way I'm describing it, this is something I'm interested in. And there's a sense that it's not purely mathematical reasons that go into choosing which axioms you use. There are aesthetic reasons. There are other things going into it as well. Yeah.
On the previous slide, when you said like a system of edge elements, does that imply that they are only considering edge being finite?
Yes.
Okay.
Yeah. Yeah. As I say, it's only a definition that works in the finite case. Okay, so I'm not really going to say any more about groups now, but this word algebra is also starting to drift a little bit more. So algebra always meant solving equations. I mean, that's just what it meant, coming from al-Khwarizmi. Because groups are linked to equation solving, then the word sort of drifts a bit on towards meaning groups. And then as groups become these more structural things, the word drifts still further to begin to cover other abstract or axiomatically defined objects that people are starting to study, often that have links back to some form of equation solving. So this is the case with structures like rings and ideals, and if you didn't do the rings and modules course last year, you won't know what some of this means, but don't worry. So we have people like Ernst Kummer, who's interested in number theory and looking at various ideas like cyclotomic integers that come up naturally in number theory, particularly if you're trying to prove Fermat's last theorem. And he's bringing up questions of unique factorization and finding that he's working in systems where unique factorization doesn't work anymore in the same way it does in the ordinary integers. So he's trying to find a way of capturing this mathematically, and indeed restoring unique factorization, and comes up with this idea of an ideal prime factor, which is a sort of extra element that you add into the system you're looking at, which then helps you to restore unique factorization. But they're very slippery things. They're not defined directly, they're defined through their divisibility properties, and they're quite hard to get hold of. So then Dedekind comes along a little bit later on, and he says, well, instead of thinking about trying to get a hold of these slippery ideal elements, well, let's just think about the set of elements that they divide. And this is what becomes the notion of an ideal that you may or may not have learnt about in connection with rings. And so the sort of theory of prime elements versus irreducible elements, this kind of theory of domains, integral domains and so on, has its roots here. In very concrete terms, I should say. So neither Kronecker nor Dedekind was working with an abstract system at this stage. They're working with specific number fields and developing these ideas that are then taken in a more abstract direction. And this happens from those early axiomatizations. So Weber, with groups, as we just saw, he also produces an axiomatization of fields, which looks very much like the thing that you learn in Analysis 1. Other people are contributing. So Ernst Steinitz is an author that I will come back to when I talk about linear algebra in a couple of weeks. He has this quite nice booklet in 1910, which, on the surface of it looks like it should be about the theory of fields, but it's got so much else in there. There's vector spaces, there's a crystallization of notions of linear independence, there's all kinds of linear algebra going on in there. And then rings are sort of a latecomer in terms of their abstract formulation. So people sort of have a go. Dedekind and Hilbert are working with specific rings, and then we sort of get an axiomatization that eventually emerges in the 1920s, which I'll mention in a second. And this idea of abstract algebra being an inherently axiomatic thing gives rise to another instance of perhaps something that doesn't, a mathematical group that doesn't really go anywhere. So the American postular analysts in the early years of the 20th century were concerned with the study of systems of axioms for their own sake and looking at what is the best system of axioms, what can we have a minimal system, can we have independent axioms, all this kind of thing. It sort of has a sort of flurry of interest in the first decade of the 20th century and then dies away very, very quickly. But it's part of the formation of sort of an identity for an American mathematical research community at this stage. But that's an entirely other story. So just to start bringing things to a close, I've talked about people working with specific rings, specific ideals, specific modules, whatever. Where does this actually start to become properly abstract? And well, that in many ways comes with Emmy Noether in the 1920s. So she's studying rings, commutative rings at first, but certainly studying rings. And she settles on a definition slightly different, an abstract definition, slightly different from what people had worked with previously. But one that was more suitable for what she was doing, which I won't go into. She had this line, "Es steht alles schon bei Dedekind." It's all already in Dedekind, which is sort of a very modest statement to say that everything that she was doing was already in Dedekind's work, which is not quite true. So he was looking at the concrete cases of things. She's shifting them into the much more abstract setting, a more general setting that then quickly takes off because it finds its way into a textbook. So Van der Waarden's Moderne Algebra, which is then sort of spread around the world, translated into various languages, really spreads this point of view. And of course, now it's a very dominant point of view in mathematics. So not just groups, fields, rings, but any number of other abstractly, axiomatically or not defined objects that have emerged as objects of study. Okay, so I'm just going to finish off then with a couple of recommended books. So the one on the left is very accessible. It covers algebra and linear algebra, so you might see me refer to this again in a later lecture. Sort of very nice, readable book. The one on the right is much more heavily mathematical, but also still very good picture of what people were doing in sort of developing this much more structural approach to algebra. And as I've said, this structural approach is one that's certainly emerging very strongly in the 19th century. And so next week we'll see the crystallization of the notion of a set, for example, is one of the things that really general things that comes out of this. Okay, so I'll stop there for this week. Next week I will go back to the story of analysis, real analysis at least. I'll take that as far as we're going to take it in this course, through the formalization of some of the notions that we've already talked about, up to the beginnings of set theory. And before then, though, I will see you all in the classes on Friday.